Picture this. It's 2 a.m. The blue light of your IDE is literally the only thing illuminating the room, and your coffee went cold about, I mean, probably 3 hours ago at this
Well,
point.
yeah, we've all been there.
Right. And you're staring at this wall of code, trying to figure out why an API integration is just failing silently.
The worst kind of failure.
Exactly. And you know the answer is buried somewhere in the documentation, or maybe like a Slack thread from 6 months ago, or perhaps in a server log that is literally a mile long.
Yep, just an endless wall of text.
As a software engineer, you're constantly trying to hold all these disparate pieces of context in your head at once. And usually, right when you're about to connect the dots, your brain just it just drops something. You forget the specific parameter name or the exact sequence of the callback.
Because human working memory is an incredibly finite resource. I mean, we can only juggle so many variables before a ball drops.
It's true.
But that cognitive bottleneck isn't just a human problem, though. It is the exact same fundamental constraint we run into when architecting artificial intelligence.
Okay, let's unpack this, because tonight's deep dive is all about the mechanics of AI memory. We are looking at the engine room of these large language models, specifically focusing on this concept of context windows.
Right, the context window.
Yeah, this is the ultimate metric of an AI's working memory, how much it can actively remember and process at any given moment.
Exactly.
We're going to look at the explosive growth of this memory capacity, the brutal mathematics that make expanding it an absolute engineering nightmare, and the architectural workarounds you can use today to build really highly scalable applications.
Yeah, and to really appreciate those engineering workarounds, we have to define what the context window actually is because, well, it often gets confused with the model's training data.
Right, people mix those up all the time.
Constantly. But the context window is not the petabytes of data the model read during training. It is the active workspace. It's the prompt you type in, the system instructions you configure, the history of that specific conversation, plus whatever, documents, JSON files, or code snippets you paste in.
The scratch pad.
Exactly, the scratch pad.
And looking at the early days of this architecture, like the original transformer model that basically kicked off this whole modern AI era, that scratch pad was incredibly constrained. It had a context window of just 512 tokens.
Yeah, 512, which is, a token being roughly 3/4 of a word.
Right.
Or in the context of programming, maybe a single variable name or a syntax operator. So 512 tokens is barely anything.
It's tiny.
It's perhaps a few paragraphs of text or a single moderately sized function in Python.
So if you're a developer trying to build a tool with that original model, a 512 token window is like hiring an assistant who can only read a standard size sticky note.
That's a great way to put it.
You hand them the sticky note, they read it, but if you hand them a second sticky note, they have to throw the first one away. They completely forget what was on it. You couldn't even paste in a full React component without the model losing track of the state variables declared at the very top.
And what's fascinating here is that constraint defined the entire first generation of AI applications.
Yeah, it really did.
With only 512 tokens, developers were limited to very strict single-turn interactions. You could ask it to translate a sentence or summarize a single paragraph, or maybe write a regex pattern.
But there was no deep analysis.
None. There was no continuity across a complex workflow because the model literally lacked the working memory to hold the context.
Fast forward to modern models like Gemini, and we are looking at context windows of 2 million tokens. 2 million. That is just a staggering leap. We're talking about a 4,000 times increase in capacity.
It's massive. It changes the entire paradigm of what a software engineer can build. 2 million tokens is roughly equivalent to about 1.5 million words.
Wow, so we go from an AI that can barely read a sticky note without getting amnesia to an AI where you can practically back up a dump truck full of data.
Literally a dump truck.
Right. A 2 million token window means you could drop an entire application's code base, the complete stack of AWS technical manuals, and the entire history of a project's Jira tickets right onto the AI's desk all at once.
And ask it to synthesize all of that information simultaneously.
It's wild.
You are no longer asking an AI to just find a syntax error in a single function. You can ask it to trace an architectural flow across dozens of interconnected microservices.
Yeah, you can feed it the current server logs, the documentation for the third-party API you're integrating, and your source code, and ask it to find the discrepancy between the three.
Exactly. It enables true multi-document reasoning.
Here is where it gets really interesting, though. Because as an engineer, you hear 2 million tokens, and your immediate instinct is, well, why stop there?
Right, why not more?
If a 2 million token workspace is this powerful for debugging and synthesis, why do we cap it at all? Why not build a model with a context window of 1 billion tokens? Let it ingest the entire internet in one prompt.
I mean, that's the dream, right? But this leads us directly into the physics of computation and the mathematical limitations of the transformer architecture itself.
The dreaded math.
Yeah, this is the core engineering bottleneck. It's known as the quadratic scaling of attention. To understand why we can't just turn a dial to infinity, we really have to look at how the attention mechanism actually works under the hood.
Let's break that down for the listener. What does quadratic scaling actually mean, like on the actual server rack?
Right. So in a transformer model, the attention mechanism is the mathematical process that AI uses to figure out which words or tokens relate to which other words.
Okay.
It does this by creating a massive matrix where every single token in the context window has to mathematically compare itself to every single other token.
Every single one.
Every single one. It generates a query and compares it against the keys of all other tokens to assign an important score or like a weight.
So just to keep the math simple, if you have 10 tokens in your prompt, that's 10 times 10 comparisons, 100 operations.
Exactly. And if you double the input to 20 tokens, it's 20 times 20.
400 operations.
Right. You double the input, but the compute went up by a factor of 4. Doubling the context quadruples the compute.
Wait, I want to look at the practical implications of that for a second.
Sure.
If a developer is building, say, a log analysis app, and they decide they want to feed in twice as many server logs to give the AI more context for a critical bug.
Very common scenario.
Right. The back end doesn't just work twice as hard. It has to do 4 times the computational work, consume 4 times the energy, and use drastically more memory.
Yep.
That sounds like a fast track to completely bankrupting your cloud computing budget.
Oh, it is. It is entirely unsustainable for scaling production applications.
Wow.
If you scale that quadratic curve up to thousands or millions of tokens, the compute graph doesn't just rise steadily, it hockey sticks straight up.
Just vertical.
Exactly. The physical RAM on our best GPUs simply cannot store the intermediate calculations required for that massive matrix multiplication. The memory requirements just explode.
But clearly, we do have 2 million token windows available today. I mean, the servers haven't melted down.
True.
So how are engineers cheating this math? There must be, like, architectural shortcuts happening under the hood to bypass that quadratic bottleneck.
Oh, absolutely. Engineers are implementing brilliant optimizations because, well, while you cannot change the fundamental laws of mathematics, you can change how the hardware processes the math.
Right.
And you can take calculated shortcuts. One of the most critical breakthroughs in this area is an algorithm called flash attention.
I've heard of that.
Yeah.
How does flash attention actually bypass the bottleneck?
It attacks the problem at the hardware level. The bottleneck in GPU computation isn't actually the processing cores, it's the memory bandwidth.
Interesting.
Moving massive matrices back and forth between the GPU's main memory, the high bandwidth memory, or HBM, and the ultra-fast processing cache, the SRAM, it just takes too much time.
So the data transfer is the slow part.
Exactly. The cores basically just sit idle, waiting for data.
So the processor is essentially twiddling its thumbs, waiting for the giant matrix to load.
Precisely. Flash attention solves this through a technique called tiling.
Tiling, okay.
Instead of trying to read and write the entire attention matrix to the slow main memory, it breaks the matrix down into smaller blocks or tiles. I see.
It loads a tile into the ultra-fast SRAM, computes the attention scores for that specific block, updates the final result, and then moves to the next tile.
That's so smart.
It is. It drastically reduces the number of times the GPU has to read and write to the slow memory. It's a hardware-aware algorithm that massively speeds up the context processing without losing any mathematical accuracy.
That is fascinating. It's basically optimizing the physical supply chain of the data inside the chip.
Exactly.
But, I mean, hardware optimization can only get you so far if the math itself is still quadratic. What about algorithmic shortcuts?
That's where techniques like sparse attention and linear approximations come into play.
Okay, what's sparse attention?
Sparse attention looks at the massive matrix
Yeah.
and makes a calculated assumption. Does every token really need to compare itself deeply to every other token?
Probably not.
Right. If you have a 1,000,000-word document, the word at the very end probably doesn't need a strong mathematical relationship with a preposition in the third sentence.
Makes sense. So it selectively masks out relationships.
It forces the model to only calculate attention scores for, like, a specific sliding window of nearby tokens, or perhaps only highly relevant keywords, ignoring the vast sea of unrelated data in the prompt.
Yes, and linear approximations take it a step further.
That's so.
They use mathematical kernel functions to approximate the complex softmax calculations required by the attention mechanism.
Okay, now we're getting into the deep math.
Oh, I know. But simply put, instead of computing the full n-squared matrix, they find a mathematical projection that allows the compute to scale linearly,
Oh, wow.
meaning doubling the context only doubles the compute.
That is huge. So we have these incredible engineers pulling off miracles with memory tiling and sparse algorithms just to give developers these massive context windows.
Yep.
But, and this is a really critical pivot, even when you use flash attention to physically process a 2 million token prompt, bigger is not automatically better.
Not at all.
There is a documented behavioral quirk in how these models actually read that massive amount of text.
This touches on the crucial difference between capability and reliability. Just because a model has the capability to ingest 2 million tokens doesn't mean it perfectly comprehends or weights every single one of those tokens equally.
This is the lost in the middle problem.
Yes. It's a highly documented phenomenon across almost all large language models. The models do not allocate their attention uniformly across a massive prompt.
So they play favorites.
Essentially. Information that is placed at the very beginning of the prompt or at the very tail end is generally recalled and synthesized with very high accuracy.
Right.
But information buried dead in the middle of a long context is far more likely to be completely overlooked.
It's remarkably similar to how a human crams for an exam.
Oh, totally.
You stay up all night reading a 500-page technical manual.
Mhm.
The next morning, you remember the first chapter perfectly because your brain was fresh.
Yep.
You remember the conclusion perfectly because it was the last thing you read before you closed the book. But chapter 4, that is just a complete foggy blur.
That analogy holds up so well, but we can actually explain why this happens mathematically within the AI.
Okay, let's hear it.
It comes down to attention dilution. When the model calculates the attention scores for 2 million tokens, it pushes those values through a softmax function, which essentially turns them into probabilities that must sum to 1.
So you have a probability mass of exactly 1.0, and you were trying to divide it across 2 million different tokens.
Exactly. The probability mass gets spread so incredibly thin that the middle tokens become statistical noise. Their attention weights drop to near 0.
Wow.
The model's architecture also inherently anchors heavily on the absolute positional encodings at the start of the prompt, usually where the system instructions live,
Right.
and the end of the prompt, where the user's specific query usually lives. The middle just gets squashed.
Think about how developers typically construct prompts, though. This mathematical quirk is incredibly dangerous for application reliability.
Very dangerous.
Usually, you put the system persona at the top, like you are an expert senior back-end developer. Then you dump a massive amount of reference data in the middle, 3 different JSON payloads, a massive server log, and the API documentation.
Just a huge sandwich of data.
Exactly. And then at the very bottom, you append the user's query. Why is the authentication token returning null?
And if the crucial variable or the specific API key format or the precise error code is buried in line 5,000 of that server log sitting right in the middle of the prompt, well, the model will likely fail to see it.
It just skims right past it.
Yeah. It's not that the token fell outside the context window, it's that the attention mechanism mathematically deprioritized it into oblivion during the synthesis.
So let's look at what this means for the software engineer architecting a solution today. You have this incredibly powerful 2 million token workspace available.
Right.
But if you actually try to fill it up with a brute force data dump, A, it costs a fortune in compute latency and token fees, and B, the model might just ignore the most important piece of data anyway because it got lost in the middle of the probability distribution.
Which is why relying purely on massive context windows is often considered an anti-pattern for production software.
An anti-pattern, really.
Yeah, it's an expensive brute force approach that is prone to behavioral degradation. To build reliable, fast, and cost-effective AI applications, the industry has shifted toward a different architecture entirely.
And this is the workaround. If stuffing the context window is mathematically punishing and behaviorally risky, how do we give an AI access to a massive code base without actually putting the code base into the context window?
Right.
This is where we talk about retrieval augmented generation, RAG. RAG.
Marriage is arguably the most fundamental architectural pattern for an AI engineer to master right now. It is a complementary approach that gives models access to vast external knowledge bases, completely bypassing the need for an infinite context window.
To put it simply, instead of forcing the AI to memorize an entire library of information in one sitting and hoping it doesn't forget the middle of the stack, RAG is essentially giving the AI a highly efficient semantic search engine.
That's the perfect way to frame it. With RAG, you take your massive code base, your millions of server logs, and your encyclopedias of documentation, and you don't send them to the language
You'll
model.
hold them back.
Instead, you process them externally. You break all those documents down into smaller chunks, and you convert the text into high-dimensional numerical vectors, also known as embeddings.
Let's pause on embeddings, because that's really the secret sauce here. How does converting text to numbers create a semantic search engine?
An embedding model analyzes the text and maps its underlying meaning to a coordinate in a multidimensional mathematical space,
How many dimensions are we talking?
often 1,500 dimensions or more. In this space, concepts that are semantically related are physically close together.
Okay, give me an example.
So the vector for the word authentication will be mathematically very close to the vector for login or oath, even if they don't share any of the same letters.
Oh, that's clever. So you embed your entire code base and store all of those coordinates in a specialized vector database. The data lives completely outside the AI's internal memory matrix.
Yes. And here is where the architecture comes together. When a user asks a question, like, how do I implement the new oath flow? Your application takes that specific query and runs it through the exact same embedding model.
It turns the query into a coordinate.
Exactly. It turns the query into a coordinate.
And then it just looks at the vector database and says, find me the 3 chunks of documentation that are physically closest to this query's coordinate.
You got it. It calculates the mathematical distance, like cosine similarity, to pull the most deeply relevant paragraphs.
Precisely. The system retrieves just those top 3 or 4 highly relevant chunks of context.
Then, and only then, does the application open up a small, highly focused context window for the language model.
It pastes in those few paragraphs, along with the user's question, and asks the AI to synthesize an answer.
That is an incredibly elegant solution. By utilizing RAG, you are completely bypassing the quadratic compute bottleneck because your context window remains incredibly small and cheap.
You aren't processing 2 million tokens, you're processing maybe 2,000.
Exactly. And you completely bypass the lost in the middle problem because there is no massive middle to get lost in. You are only feeding the model the exact, highly concentrated signal it needs to generate the answer.
It represents a massive shift from pure generation to highly orchestrated retrieval.
It really does.
It shifts the heavy lifting from the AI's internal attention mechanism, which, as we discussed, is expensive and constrained, to an external database system, which is fast, cheap, and infinitely scalable.
RAG allows developers to build applications that feel to the user like they possess infinite memory, without having to actually compute an infinite context window.
Looking at the bigger picture, the journey we've covered here is wild.
It really is.
We started with the original transformer architecture, sitting there with its tiny 512 tokens sticky note, unable to hold on to the context of a single script. Then we explored the massive scale of modern AI, with 2 million token workspaces that let you drop entire repositories onto the active scratchpad.
But we grounded that expansion in the brutal reality of physics. We explored the quadratic scaling of attention, where doubling the input quadruples the compute, and how hardware optimizations like flash attention's memory tiling are required just to keep the servers running.
And even with hardware optimization, we saw the behavioral flaws. The attention dilution that causes the model to act like a sleep-deprived student, completely dropping the vital variables buried in the middle of a massive log file.
Which naturally led to the adoption of retrieval-augmented generation, the pragmatic architecture that relies on vector embeddings to retrieve tiny, targeted snippets rather than forcing the model to process the entire dataset at once.
It really changes how you approach building an AI feature. You're not just a prompt engineer trying to cram data into a text box. You are a systems architect.
You are balancing vector database retrieval latency with LLM synthesis.
Exactly. But of course, the context window and the retrieval mechanisms are only part of the equation. What happens before the developer even types the prompt? How does the model know how to write code in the first place?
That is the next logical step in understanding AI mechanics.
For sure.
Next time, we are shifting away from the active workspace and diving into the foundational training. We'll be examining the massive data sets, the complex curation strategies, and the aggressive quality filtering that determine what a language model actually knows and how its underlying reasoning capabilities are shaped before it ever sees a user prompt.
I'm really looking forward to unpacking that. But before we wrap up this deep dive, I want to leave you, the listener, with a final thought to mull over while you get back to your IDE.
Yeah, think about this.
Think about the trajectory of this technology. If an AI can technically hold 2 million tokens in its working memory, but it loses track of the middle due to attention dilution, and we successfully bypass this limitation by using Array to just mathematically retrieve the exact snippets we need, at what point does AI memory stop being about pure computational capacity and start becoming purely an exercise in search optimization?
That's a great question.
If the real bottleneck to building a smart application isn't the size of the AI's brain anymore, but the quality of your vector embeddings and how well you chunk your data, how does knowing those specific blind spots change the way you'll architect your very next feature?
Will you keep trying to cram more data into the prompt, or will you focus on building a better search engine for your AI?
Some to think about while you track down that silent API failure. Until next time, keep digging.